Right. Okay, let's crack on and let's start with this lecture. So, yeah.
The lecture slides on the website.
Oh. Yeah, I have. Can't see. What's this one called? L48. And it's 07. And then do prep teaching. Physical. Where are they in? Are they in lectures? Nope. Slides. Yeah, here they are. Yeah. Right, now they should be there, I think. Good stuff. Cool. So today we are going to talk about probabilistic numerics-ish. So we're going to try and extend the concepts that we talked about last time and try and generalize this a little bit, and hopefully you'll see that, well, you'll definitely see that I'm very excited about this, even though apparently I can't spell numerics, but I'm very excited about this kind of stuff. So hopefully I get a notion you'll get a notion of why I am excited about this and why you should also be excited. But let's just begin with a couple of things to begin with where we have been. So we started about talking a lot about uncertainty, or ignorance, or beliefs, and all these things. And in the beginning, we saw this embedded notion of the scientific principle in terms of the concept of marginalization. So what we saw was that when we took our beliefs, we took our data, we combined these things by marginalization, we saw this notion of how we can update our beliefs. Cool, that was very nice, but it was done in one operation for us. And then last lecture, we talked about, okay, what can we do to externalize this learning process itself and get a bit more handle on it? And we did that in terms of the base of the example that we had. And I hope that you felt that that lecture was it was quite natural. It wasn't any rocket science that we actually saw. We had this notion of saying, cool, I don't know what the function is, I want to search this. And now we do this in an active learning loop where we were continuously balancing what we knew, our exploitation, to the exploration. And we saw that. Cool. So in a way, what I wanted to get to with this concept is that what do we actually do with uncertainty? What do we do with what does it allows us to do when we parameterize our ignorance about the problem? But it allows us in one way to reduce our ignorance, right? That's the whole aim of these things. And we saw this now in two different ways. One, the very in base rule in itself, and we also saw it when we took control over it in the active learning setting. So what are we going to do today? Well, today is actually the last lecture that I'm giving in this course. So I'm going to tell you a little bit about probabilistic numerics, but there's also a couple of other things that I wanted to tell you that I was like, I can't leave this course without talking about this. So it ends up a little bit of a potpourri about a couple of other things as well. Hopefully you'll be okay with that. So it's probably going to be a little bit less structured than normally. So the first thing that I felt, oh, I can't leave without talking about this is the marginal likelihood. Because you saw this, I showed you this plot or this slide before, probably on the first lecture, where I said, you know, this is a completely uninteresting mathematical object, but when you start adding semantics to it, it becomes really, really cool. And we talked a lot about likelihoods, we talked a lot about priors, and we talked a lot about posteriors, and hopefully you get all these. Then there was this denominator term, the evidence, which I kind of avoided talking about at all. And I kind of used phrases that, it's this normalization factor that adds lots of issues to us. But actually, this is the coolest object of them all, right? This is the grand, cool, super exciting thing. So I'm just going to give you a little bit of a notion of this object. So we showed this slide at one point, and I said I tried to give a visualization of what the evidence actually means. In this case, we had this really simple likelihood. We had a distribution over y, so over our data, that was indexed by w. But what that said was that if I pick a world, w, I pick a specific line, w, what do I think the world looks like? Okay, so that's each one of these distributions. These are two different w's. Okay, and then we said, okay, if this is then how one world, I believe one world manifests itself, what do I believe the world actually looks like? Well, that was our prior. Like, what is my strength of belief, my ignorance about the system itself? Okay, we have three different ones here. If I now say, cool, I'm now going to integrate out all my beliefs and take every possible world averaged according to the strength of belief I have in them, I end up with this distribution. Okay? Then I end up with P of Y, which is the evidence. So now it's an easy way to think, cool, so what I do during marginalization, I remove the dependency of a variable. That's the opposite of what you're doing. You're taking that dependency, everything you know in here, and you bake it into everything, right? So you're basically taking the effect of W everywhere. It's just that you don't have it parameterized. You don't need to specify it, but this distribution clearly is massively affected about this, right? So my joke is this, right? The most respectful thing you can do to anyone is to marginalize them, right? So the joke is this, that you should go home and tell one of your friends to just test if they're a machine learner or not, and say, you know, I really respect you. I really care about your opinion. So I've completely marginalized you from my life, right? Because that is the most respectful thing you can do to them, right? Because now you take it into account everywhere. So let's just see this in terms of an example. So let's say I have two models. We talked about both of these. We have a linear model, so it's a line. That's two parameters plus some noise, right? And then I have a basis function model, which has 6 basis functions. Now the question is, wow, which one of these should I choose? Well, what can you compare about these models? Well, they're really hard to compare because they've got different sets of parameters, right? Now let's look at the evidence for this. So this is the plot we saw before. Take a couple of lines. I had some belief. Now I can give the evidence. It looks like this. Okay, just lots of lines going like this. And then we take the other model, and now it looks like this. This is another P of Y, right? Now, if we compare these two models, these are both distributions of what I think the world looks like, right? Coming from two different modeling assumptions about something. And you can see that these both look fundamentally different, right? If I now start seeing the world, if I start seeing observations here, this one here will say, oh, you know what, I don't think that makes sense at all. It's going to have a very low value, while this one is probably going to have a much higher value, right? So now, these two are distributions that we can compare because they're both just distributions over the data space, over Y in this case. And the cool thing about these is that probabilities need to normalize to 1, right? So if you're good at something, that implies you have to be bad at something else. So probabilities are effectively a zero-sum game, right? You're very good at something, that implies you're bad at something else. And we can exploit this when we compare these two distributions by doing model selection. But often you will hear a notion that if you look at the marginal likelihood, it implements the notion of Occam's razor. This plot here is usually referred to as the Mackay plot because I think it was in David Mackay's PhD thesis from 1991. The notion here is that I have 3 models. Each one of these is the marginal likelihood computed under that model. So now you have, on this axis, you have the data sets. Okay, let that be abstract at the moment, but you have all the possible things that you can observe. Okay, so then these are sorted, arranged to the what you think is a simple data set to something that you think is a complicated data set. We'll come back to what that actually means. Then, if I have a marginal likelihood, it could have millions of parameters, doesn't matter, I've integrated them all out, right? And then I have one model that places distribution everywhere, right? That means it explains everything. It says, oh, that's fine, yeah, sure, okay, I'm happy about this. That implies that it also has to be low everywhere, right? Because it explains many things, this zero-sum thing, right? So what that means that if I now would see data here, this is what I actually observe. Which model should I pick? Well, I should pick the one that has the highest marginal likelihood, because that is the model that explains what I see, but as little else as possible. Right? And this is the notion, if you like philosophy, Karl Popper talks about this, and he says the quality of scientific explanation is how easy it is to falsify. Right? A theory that explains everything has no value. Right? This theory here pretty much explains everything, so therefore it has a very low scientific value because you can't falsify it. It's very, very hard to falsify this model. Right? Cool. So that's then the notion, possibly, of Occam's razor. So Occam's razor then, we know, says all things being equal, the simplest solution tends to be the best. We can then use the marginal likelihood to select models if we got multiple ones of this. So now there's a thing which I didn't state specifically, and that's this notion, what is simple? I said, oh, use to range everything that's from hard to simple on this axis. Well, is the concept of simplicity objective? No, I think it's very subjective. If you haven't seen this film, Behind the Curve, about flat Earth people, it's fantastic. It's on Netflix. Every argument they do in this film is about Occam's razor, right? Because they say, oh, clearly the Earth can't be a sphere because of this and this and that. That's such a complicated argument. And I think most of us will say, oh no, that argument is really complicated. So the notion of simplicity is not at all objective, right? And what that leads to, when you look at this graph here, is just how do you actually sort things according to this? What's the actual x-axis? My notion is that the x-axis is what you specify with your prior. You're effectively saying, I have a prior, my prior itself induces what I mean by simplicity. Right? So it's definitely not an objective measure. Okay, so then what I just wanted to show is that to an introduction, what we're really going to talk about today is just the strength, what you can do with beliefs. So look at this. What we've done this with GPs, we've done regression. So then what we said is that we have a Gaussian process prior, which is indexed by a variable x, right? We have this index variable that we said, oh, I can look at what the slice, the distribution is at the specific value, okay? So now, let's say that we would want to do unsupervised learning. I put unsupervised learning within quotes because I think it's a misnomer. How do you do unsupervised learning? It feels very weird to me. Some people say unsupervised learning is hard. If you've ever trained a dog, it's much harder to make it do what you want it to do than make it to do whatever, right? I can make my dog do unsupervised learning any day, right? But I'm pretty sure I don't want it to eat my shits, right? Oh, supervision, right? Great. Unsupervised learning, I think, is a misnomer, and it should be called more supervised learning. Cool. So let's say that we want to do this. Let's now say that I just want to learn this distribution. So I have some output data. I have no input data. So I want to do regression by just saying, cool, I want to find both the function and the input locations to this. Well, this is actually turns out to be very easy. Look at this problem here. Just trying to show the problem that we're trying to solve. I have some y values. So let's think about these as an abacus. And my question is, can I give each one of these an x location and bind them together with a function? Right? That's my question. Right? Well, that's not particularly hard to do, right? Because look at this, the notion of simplicity that I talked about in terms of the marginal likelihood. So you specify now a prior on what the function is. Well, I can give you that solution, right? And then you say, no, I don't like that solution because it's not smooth enough. Okay, cool, I'll give you that one. Oh, I don't like it. Now, you see how a prior, in this case, a distribution, induces a notion of simplicity as well, right? Because you can have a prior and you can evaluate each one of these possible explanations under that and say, oh, I like this one more than that, right? So by just computing this marginal likelihood, I can test effectively what I do is I test all these possible combinations. Here I've just fitted the GP to a specific set of X. You integrate all these things out and you end up giving you a distribution over both the location X and what the function fits with it. So What then I wanted to do, hopefully you got a little bit of the notion that this isn't picky on, this is the same thing again. I will specify my ignorance or my beliefs about all things. The same handle I can use churn. Now we're going to take that one step further. So what I hope is that we're going to try to communicate the strength of the things you can do as soon as you parameterize your ignorance, you parameterize your beliefs about something, how many things you can actually address with that. So let's then talk about things I believe in. So last lecture we did this. We took this function and we said that I don't know what this function is, but I can evaluate this function and I want to compute the minima of this function. So let's think, what is the minimum of the function? Well, it's a characteristic of this function. What we're going to do now is that we're going to extend this notion and say, can we be probabilistic? Can we do the same machine learning reasoning about other concepts of the function? So, yeah, sorry, we did this optimization. So let's abstract this a little bit. This notion here, what I'm drawing now is not a graphical model, it's a more abstract graph. This comes from a paper from 2017 by Cocaine, Oates, and Sullivan, I think. It's an absolutely fantastic paper that I really recommend you to read. It's about 50 pages long, but it's very, very cool, I think. So, what they do is they say this. So when we do machine learning, any type of machine learning, what we're interested in is that we have some quantity of interest, right? Previously, that was the minimum of a function. It could be fitting the density to a function. It could be anything. But you have a quantity of interest that you're interested in. Then we have some form of latent variable that we don't know about, right? Here, I've just written that as a distribution, but let's say that that could be the function itself in the previous case. I have the function, what I'm interested in is a minima, there's a clear operation, this is the operator f that takes me from whatever I have to, or whatever this latent quantity, to the quantity of interest f hat. If you do regression, this would be, have a joint distribution of the data. Now what I want to do is I want to find a conditional distribution of this. Then what we said, right, in the first lecture that I gave, I talked about statistical learning theory. I say, well, the trick is that we don't know this. We don't have this quantity. So what we do instead is that we take some sample set, S, and then we design an algorithm to try to take us to this quantity of interest, right? Okay. That was what we did. So we said in the regression case, I don't know the function, but I have some observations of the function. Let's fit the model, let's do an algorithm, and let's try and fit this function in itself. Okay, then we did last lecture, we said, well, actually, that S here is not static anymore. I also have what we call an information operator, which says, you know what, I can actually control what data I get. So I can go out from this latent quantity that I don't know, the function that I don't know, I can go and sample and say, I want to know what the function is there. And then I can design an algorithm, just as we did, and then I can try and find this. And the task of any machine learning system is to make this graph commute, right? If I can make this step and this step match this step, right? Okay, so what we're going to try and do now is we're going to take another quantity of interest of a function, namely its integral, and we're going to look at that. And we're going to see, is it possible to treat that as a machine learning problem? So let's say if you had a function that, let's say we even know this function, right? I have a function up here. I know this function. I know the integrand. But let's say I can't do the integral for some reason. This is something that's not analytically possible. I can't do this. What I can do is I can query this. So I can design a query operator. Maybe what you do is you just take a uniform grid, right? Plot these points. Then you can design an algorithm, something like this, some form of probability rule, and you can get an estimate of this, right? So it's not rocket science. If you've done numerical analysis, you've seen lots of these things, right? Okay, so that's an example of this. So now we're going to try and look at, can we do this with machine learning instead? Can we be a bit statistical about this instead? Can we find these handles to input our knowledge into this, so we can churn this handle that we've designed? So here is a function that we actually don't have an analytical integral for. So what I could do is that I could do this quadrature rule, and you take discretize the space in this way, or I can do it in this way. Each one of these will give me different values, right? Because I fit the function differently well. So then let's think about what each of these computations were. So a numerical method estimates a function's latent property given the result of the computation. So let's think about that then. So statistical inference takes data in the form of measurements of observed variables and aims to return predictions of the quantity of interest. Right? That's what we've been doing so far. A numerical algorithm takes data in the form of evaluation of computations and aims to return predictions of the quantity of interest. It's exactly the same thing, right? There's nothing different between these two statements. It's just two different things they observe. It's either a measurement, but now we just consider the output of a computation a measurement. Right? There's really nothing different to these. So should we then think about computation just as statistical inference? And that's what I'm going to try to convince you about today. Why would I want to do this? Well, to begin with, if I think about statistical inference, this allows me this whole framework of beliefs, of ignorance about all this philosophical stuff that we talked about to fit to computation. So that means I can start thinking about, why should I use this algorithm? Well, this algorithm implements this assumption. Oh, great, perfect. And I have that in the language of probabilities. Secondly, I can most likely use algorithms much more efficiently that are expensive, right? Just think about this one here, right? If I actually have a probabilistic notion of this, I could start doing explore and exploit of how I put this grid up, right? I wouldn't just do this one here and say, oh, delta X, they're all just at the same place. Maybe I can actually do inference in the same way as we did in base op, right? We were really clever of how we chose the next point to sample. So that would be super beneficial. The next thing is, most of these numerical algorithms that we use, what we know with the quadrature rule is that it has some convergence. Towards infinity, it will be correct. Well, great. We don't work in infinity. It's very expensive to run a computer to infinity, right? Could I instead get the notion of possibly, say, a variance over what my result is? Now I can say, you know what? I need you to do this computation up to this level of granularity. Then you're fine. I don't need this further on. And then the final thing of this, which is not on the slide, I think it's in the summary, is that if I'm uncertain about all this other stuff that I do, right? My measurements, my simulator, all this, why shouldn't I be uncertain about my computation, right? Why would I waste doing really precise computation on measurements that are crap, or vice versa, right? It's all about balancing these things jointly. So therefore, it's very beneficial to look at computation in the same framework. So Another thing then, to align to what Neil talked about, we just found this quote, which is very old, from von Neumann, who said this thing. Round-off errors are strictly very complicated, but uniquely defined number theoretical functions of the input. Yet our ignorance of their true nature is such that we best treat them as random variables. So this is this notion of that even if you have, from the game of life, right, even if you have these very, very clear defined rules, right, like rounding errors in a computer, actually you're better off, because it's so complicated to treat all this the whole way properly, you might be better off treating all these things as random, right? And that is another motivation for this. Cool. So what we'll try to do now is we're going to try and do this for integrals. So we're going to talk about then, for the field, here I spelled it correct, that's called probabilistic numerics. So the integral that I showed before was this one. So I have this thing here. This is something that I can very quickly, easily evaluate the integrand, but this integral I can't compute. I have something which is fully specified and deterministic. I know that this is deterministic, but I can't compute this analytically. I don't have an analytical form for this. However, I know quite a bit about it. I know that it's always positive, right? That function is always positive. I also know that this much simpler function, e to the power minus x squared, is always above this function the whole time. So I can bound this thing from two ways. I actually know a lot. So why would I just throw a numerical computation without knowing that information? Right? I should use that information. And now, what we could do, what do we do when we have something that's complicated, either because of rounding errors, or we have something that's complicated because we just don't know? Well, we use emulators, right? We put something that we know how to compute, and then we try and fit this thing to the intractable. So, ideally, what I would like, right, what the ideal thing that I would really want to have is this object. I would like to have a distribution that says, this is the probability of my integral, given that I've seen this data. And now we could apply all the stuff that we did in base of, exploration, exploitation, all this funky stuff, to find the data points to minimize the variance, for example, of this integral. We can do everything that we have, right? So let's just think of what we would do. Well, we would do this with an emulator. So I'm going to be a little bit brief on the math here, but I hope you get the notion of this. So let's take this function here, and then I specify a dp prior. This dp prior is really stupid. It doesn't even contain the information that I knew about the function. I've just taken some smooth thing, right? Okay. Then what I've done here is I've computed a histogram of the integral of each one of these. Okay. So now what happens if I see some data? Well, this distribution, there's now less and less variance in this, which is going to lead to less and less variance of the integral, right? So I see some more data, chop, 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 one more. Now, each one of these are functions that I can integrate, because we can actually integrate it out in the process. And now, this here is the integral. Right. Does this make sense? It's the same thing as before. I just fit the GP to this thing, and then I integrate that emulator instead. I do all the computation on this simpler object, and I use my machine learning handle to just fit this. So what you actually do, and the cool thing about this, because people are very excited about these kind of topics at the moment, the paper that actually proposes what I just did in a proper way is from 1991. There's also one from 1988, This is a fella called Tony O'Hagan, who is now retired, but was up in Sheffield for many years, and has written all sorts of cool stuff and no one actually picked up. If people are ahead of its time, I think Tony O'Hagan is definitely one of those people. That paper I can totally recommend to have a look at if you want to know the details behind this. It's written in this really nice storytelling way. One author, oh, it's really, really beautiful. And no one seemed to pick it up until 40 years later or 30 years later. So, what Tony then said is that what I would want to do this, is that I know something about the function, potentially. So what I'm going to do is that I want to derive the joint distribution of the integral and the values that I see of the function. So then he says, okay, cool. I am going to say that if I knew the function, then I can compute the integral. This is this distribution here. And then I have a likelihood function that says, cool, if this is the function, how likely are observations on the function? And then a GP prior here. Then what he did was that he said, okay, I'm going to work in this in a completely noiseless case. So what he says is this. I'm going to pick a delta function for this, which says that if I know the function, all of these functions that I'm going to pick are functions that I can integrate. So this here is trivial. This is the delta function. It just says the integral is this. This is the function. Oop, right? Then he also says there is no noise in my observations. So if I have a y value, it comes directly from f. If you had noise, you would just add a normal Gaussian likelihood here, for example. And then I have the GP prior here. What this formulation leads to is this. It basically says that the integral and the observations are jointly Gaussian. And they form a Gaussian process that looks like this. So you have the normal, if you look at, oh, sorry, these should be the other way around. This there corresponds to this one. So I have y, so the values of the function. I've specified the normal GP prior. It has this mean and this covariance. And then, because Gaussians are linear or closed on the linear operations, the integrand will have this mean, and then it will have this covariance. So now I've specified this. The only thing you need to do now is that you need to do the normal conditioning operations as we did before when we predicted points, but you now just want to predict this one. Then you have this. And this here, because the integral is just one value, right? This is just the univariate Gaussian. So, what you can then do, and this is very cool, is you can now say, okay, let's design a strategy for where we should pick points next. You can do a very silly thing, and you can say, I want to minimize the variance of the integrand of the function. That's not really what you want to do, because the function might be very low, and you don't care if it varies very, very low. But what you can do is you can also look at the variance of the integral itself. You can say which point, because effectively you've modeled this distribution. That distribution turns out to be Gaussian for a Gaussian process. Now you've said, cool, which points should I evaluate to shrink that as quick as possible? That sounds like a very sensible thing to do, right? And now you can effectively just do Bayesian inference, but you're actually doing this over a computation. So, does this make sense? Does it feel like it was very different? I can get to this step, like, I don't give you the math for this. But if you believe me on this step, does this make sense? So what I want to try and get to is that this is not rocket science. That actually, I'm just studying the values of a computation. They're exactly the same as observing anything else. It's the same as measuring a temperature of something. I'm now just measuring the output of a computation. And in this case, I had a computation that is analytically intractable. So what I say, can I fit something that I can compute to this instead, and make sure that I try and reduce the gap between those two? That's the only thing we do, right? Okay, so now we're going to go even quicker to the next step. So in this case, my example here, I just put a really stupid DT prior. I didn't think much about it at all. I coded it up last night, so I just picked an RBF kernel and didn't do anything special. But clearly, you can think about the GP that you actually put in. So now we're going to put in a very weird GP. We're going to put in a GP that gives us samples like this. The GP with 0 mean and this covariance function. This is called a Wiener process. So this is really weird. These are the samples from this. What it is, it's actually a piecewise linear function. The piecewise linear function that just goes like this, right? So it has this divergence that goes around like this. Okay? Then I'm going to do the computations that I did before. And I'm going to say, I'm now going to compute the mean, the expected value of the integral from this. What's that? Does that look like a sensible way to estimate an integral? That's the trapezoid rule. It's the first thing you get when you learn, like when you kind of do numerical analysis and you kind of think, oh, how should I compute the integral of this? Well, I take some points and I connect them with lines, right? Okay. I'm quite excited now. Hopefully I can communicate how exciting this actually is. So that thing there is probably hundreds of years old. Now we just derive that thing through a probabilistic model. So we just derived a 100-year-old algorithm through a probabilistic model. Okay, why is that relevant at all? Well, it's relevant because I derived it through saying something about the function that I was going to integrate. Right? Remember this statement that I said in the beginning. Why would you want to treat things probabilistically? You want to treat things probabilistically to be able to choose the algorithm that's right for the problem that you're solving. Well, here we made an assumption about how the function looks like, which led to an algorithm for computing the integral. Number two, that's just the mean, right? There's no variance in there. We need variance in order to do explore and exploit, right? Well, cool. How do you choose the x points in this? Well, if you do numerical analysis, no one's going to tell you that, or they're probably going to give you some weird heuristics for doing this. Now you have a probabilistic model to do this in. You can say, which point should I pick in this case in order to reduce my variance? That's really cool. So we can now do inference, probabilistic inference over where I should pick x. That's very, very cool, I think. So to me, this is like, at least I've been working in machine learning for about 20 years. When I started looking at these things, this was like a sliced bread moment of machine learning, because this is super cool, I think. Because we're basically saying, you know, all of these old algorithms that work really well, I can just think about them as statistical inference. All the tools that I have been taught to me, they actually provide me with this really strong framework in all this philosophy and semantic that we added. And now I can apply them to computation too. And that's really exciting. So the trapezoid rule isn't exciting, right? We know how to work that. But maybe with this framework, I can now come up with new orbital rules. Of course I can. I just pick a different DT prior, and I can integrate this out, and I can say, oh, what's this rule? Oh, no one's come up with this. And more importantly, I can say, if this is the function you're trying to integrate, this is the rule that you should be using. So let's take another numerical algorithm. Let's take minimization. So this is sci-fi optimize. minimize. So if you look at this, this is how it looks like. There's this method thing there. And these are the methods that SciPy contains. There's tons of more of these. Which one should you use? I don't know, right? We all try different ones, and then we pick the one that does the best, wasting computations, right? Because we don't even know what these ones assume. They might, there is of course assumptions in them, because otherwise they wouldn't work, right? And these assumptions are not formulated in one consistent language. If I can now make these assumptions clear in terms of probabilistic language, I would actually know which one to use, right? Another way of thinking about this, in general, there's tons of numerical algorithms for every problem that you want to solve. They work, that's cool. They give different results on the same problem, a lot of the time. Now think about no free lunch, right? They are all different because they implement different prior assumptions. But we don't know which prior assumptions they implement, and therefore we don't know which one to use, right? Now, this one, I'm ending my spiel soon, but then would you, so should you then stop using these numerical algorithms? Of course you shouldn't. They work, they're awesome. But the key thing is, if I go in my train of thought, the key thing is that if I know why they work, if I have this whole Bayesian spiel to understand how the algorithm came about, now I know that, now I can throw that away and just use the algorithm, right? So another notion of this, maybe slightly similar, I talked a little bit about supervised, unsupervised learning. We've all done PCA in different ways. PCA is a classic example of this. So everyone uses the algorithm of PCA, which is looking at this as an eigenvalue problem. The eigenvalue problem tells you nothing what this does. There's a website which summarizes crimes against data using PCA. PCA is a probabilistic model that makes an assumption that your latent space is Gaussian and that your mapping is linear with a Gaussian prior order. Then you solve that. That's a hard problem to solve. No one does that. But if you know the assumptions that leads to this eigenvalue problem, you will use it in the right way. So that's the key thing. Obviously, if you know that, you will still solve it as an eigenvalue problem. Fine. Cool. So I'm going to try and wrap up with this. So probabilistic numerics just extends the notion of statistical inference to compute. That's it. So if we think then about computation as the process of extracting some form of latent property from, say, a function, machine learning is just the statistical process of updating beliefs about latent properties. Now, most computations, either because you can't do it in time, or you can't do it at all, they're not true, right? There's some form of approximations for something. And therefore, as long as we're in that setting, computation is machine learning. That's exactly what it is. But very often, it's not formulated in this way, and then we don't exactly know the assumptions that we base it on. So the benefits then of looking at computation as a machine learning problem is efficiency. We talked about this. Downstream tasks. So the computation is just a step to something else. So now I can feed through my uncertainty about the computation further on. And then I can start learning and understanding why an algorithm works, what is the assumption within the same language as everything else. And that means we can combine these things. So there's tons of literature on this. It's a very active field. We've done quadrature. There's lots of stuff on linear algebra, optimization, analysis, basically running differential equations and so forth. There's a whole field of this, and there's actually a book coming out very soon, I hope. And there's also a new Python library coming with lots of this work in. So I got 1 or 2 minutes. So then, is Bayesian optimization, probabilistic numerics. So people debate this. The yes argument is that it's using a probabilistic model as a proxy for a decision loop. The no argument, which I subscribe to, is that it's not a probabilistic numerics algorithm because the probabilistic model is not over the quantity of interest. We go back and look at this sketch. This is me trying to do the sketch of base opt. Remember what we did? We had a function that we don't know. We sampled that function using an acquisition model. Then we got some data. What did we do then? We fitted a GP to that data. Here, we do not care about the minima. There's no notion of minima in here. Then when we fitted the model, we picked out the minima. There we go. So effectively, base opt, to me, is not probabilistic numerics because it doesn't specify a distribution over the minimum. It specifies a distribution of the function, and then we use this acquisition function hat to try and make sure that the function only models things that are actually relevant to the minimum. And that's why I call this a hack. When we do quadrature, it's completely different. So this then is, being that this is the last thing I'll probably say in this course, maybe, is that this to me is one of the problems with a lot of the things that we're doing when we're doing the type of machine learning that we have been talking about. Is that what we often do is that we do exactly the same thing as we did in base opt. So what often Bayesian machine learning is about is that we say, I got a distribution of the data that I want to do something with. I can't do that. I get some data. What I then try and do is that I try to describe the distribution of the data. And then when I can do that with some model, then I can do the same operation to get this quantity of interest. This is really, 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 really inefficient. Because you're effectively saying, let me learn everything about the world. When I've learned everything about the world, I can sure figure out whatever question you have for me. You need to put the question into the learning framework itself. And I hope quadrature was an example of that. Now we say, actually, I don't care about the function, right? I don't. I care about the integral. Only the points of the function that leads to a substantial change in the integral is relevant. And that is, I think, a very useful example. Integration is a very useful example. And with that, I'm going to end. And yeah, that's it. There's no worksheet on this. The aim was to just give you, some thoughts and a bit of inspiration of thinking about how we can draw this concept really far. Cool. Thank you very much.